Hey everyone, welcome to chapter 7, where we're going to be doing things in 3 dimensions. Since we're actually going to be working on 3 dimensions and molecules and what they really look like, in order to do that, I'm actually going to be using some different visual aids so that we can actually talk things through. I'll also still have 2-dimensional pictures, so don't worry. For you at home, what I highly recommend you do is locate something like a ball of clay. Mine happens to be pink. You could also, instead of clay, you could use Play-Doh. You could also use a gummy candy if you have any of that around, and some sort of stick-like thing. I was going to use toothpicks, but I can't find any. So the other things I found around my house were straight pens. I don't know if anybody around your house sews, but I do. So there's some straight pens, and I also found some matches. These could also work for me, so we'll see what I actually wind up using. In addition to this, I would also highly recommend, I'm going to do a lot of things on paper, so I would highly recommend that y'all get ready to make yourself a table in a notebook of some sort or blank piece of paper, because what we're about to do is walk through different shapes that molecules can take. And this actually goes really well if you will go ahead and put pen to paper and get practice at making these. Now, do notice that this does depend a lot on chapter 6, so you are still going to need your Lewis structures. So don't forget those Lewis structure skills that you already have. And this is actually also a time where your nomenclature can also come back, because we could actually tell you about a molecule in words and then ask you to tell us information about it. So all the skills you've brought before, keep them coming. This is a theory called the valence shell electron pair repulsion, also known as Vesper. The main thing about this is that we know that electrons are negative. So this should not be a big surprise that electrons are negative. And things that have the same charge repel each other. So all we're really saying is that we know that we have these bonds that are connecting covalent compounds together. And as those bonds contain electrons, they're going to repel one another. So when we're trying to think about what these things may really look like, we have this notion that all atoms are going to arrange around a central atom to be as far away from each other as possible. And that means we need 3 dimensions to get as far away as possible. We are going to be counting what we call electron domains or electronic geometries. So you're going to hear a few different terms that I'm going to bounce back and forth between, but they are going to be similar and related. So what we're going to be doing is counting oftentimes electron domains. For an electron domain, this is going to be either a bond, doesn't matter what kind, single, double, triple bond, doesn't matter, or this could also be a lone pair. These are going to be areas where we know we have electrons. So in order to do our next step, where we're actually looking for our electronic geometries, we're going to be counting our electron domains. So I know I mentioned before making your own table. In the table that you make, you're actually going to need a couple of columns. So we are going to need just a single number for the number of the electron domains we're going to be working with. We're going to go through 2, 3, 4, 5, and 6, which means there's going to be a total of 5 different electronic domains. Then we're going to draw. There's going to be room for a picture, so you might need a fair amount of space. Then we need a place for the name. This is going to be also a really important part, because this is going to be our name, our electron domain geometry. We're going to also have some space to talk about the bond angles that this makes, because our picture is going to do our best, but we're also going to describe those bond angles with numbers, just in case our picture is not as easy to understand as we would like. And then we're going to come back to this idea of possible molecular geometries, but if you have a little bit of space left over, save yourself some space so we can go back to look at the possible molecular geometries. I am going to be making these with clay. So I do recommend that you guys try this out on your own. It's a lot more fun that way. As we do this first molecule, then what you should wind up with is, yes, your ball of clay or your Play-Doh or whatever you have, and then your 2 electron domains. So now we have I'm using matches. So your matches are your toothpicks. are your electron domains, and the goal is to get them as far apart as possible. So yes, they just stick out onto either side. That's all that happens. So yeah, you could look at this end on end and it would not be very impressive, but this is what that very first structure looks like, and we just call it linear because it's a nice straight line. If we had a different visualization technique, let's say with balloons, what you'll notice now is I have two different balloons to represent my electron domains, and then my fist in the middle winds up being the central atom. So I still have a way to represent the central atom, also kind of like my head. And then I have the two balloons on either side to represent my electron domains. The beautiful thing about balloons is that these will pretty much naturally form your Vesper shapes because the balloons are desperately trying to be as far apart as possible from one another. So what you should have been able to see is we should have a linear molecule from there. So our atoms are going to be in a straight line. So this could be two atom molecules. So anytime that we have something, say like molecular hydrogen, or say we have molecular chlorine, that then again is a homonuclear diatomic, this is going to give us just two atoms, but this is also going to be true when we have three atoms and just two electron domains. So we want to go ahead and pay attention to that table. So for our table, we're going to have two electron domains. I'm going to go ahead and draw my central atom as being just a dot so that I know where things are going. And all I'm going to do is draw my two sticks out from there. It's not a perfect drawing, but that's what it looks like. And so this is linear. And we'll notice that that bond angle, I'm trying to describe the angle in between the bonds. So I'm trying to describe this bond angle. So that's going to be 180 degrees.
Into the unknown, into the unknown.
On three electron domains, and the Lewis structure might have looked something like this, where we have things that are sticking straight out and off to the sides. But remember, this is our valence shell electron pair repulsion. So these need to be as far apart as possible from each other. So we need to bend these so they can get as far apart as possible. So then you can kind of see a structure that looks a little bit more like this, where we actually have this lovely 120 degrees in between my peripheral atoms, or my electron domains in between here. Looking at our balloon example, again, the balloons do a really good job of doing this automatically. So again, I've got a central atom here in the middle, and then my three balloons go out in this lovely, as far apart as possible modality really instantly. So this is where the balloons actually do a pretty good job of showing off what this would look like. Notice also that this is still a flat molecule, so I can actually still make this be in a plane. So regardless of which one I have, even though I was so excited that we were going to be in 3 dimensions, these are actually in 2 dimensions. So these actually go still on a flat page really, really beautifully because they are actually still flat. So both the linear shape and this trigonal planar shape are flat. We're going to be calling this trigonal planar. Notice that this still says planar in here. So even though we added a third electron domain, we are still all in the same plane. This is flat. You are going to have bond angles of 120 degrees, and those 3 positions are equivalent. And again, there's different ways to draw this, but I'm going to go ahead and go with this one. So I already have trigonal planar written in there, and then my bond angles here should be 120 degrees. You should notice that since this is still flat, 120 degrees, that is the same as 360, or a circle divided by 3, because we are still in flat land right now, and so we're just taking our flat circle and dividing it by 3. For some people this is helpful, for some people it's not. It's up to you.
Into the unknown.
We're gonna see if I can get a trick to work. So this is 4 balloons, but this is not the actual Vesper shape. So what we need to do, aha, I whacked it. And as I hit it, it actually settles into the correct shape. This is a tetrahedral shape. So this does kind of have a 1 up and 3 down, or double sets of bunny ears, depending on how you want to look about this. The central atom is again in the middle. And we'll come back to this balloon idea. This is a 3D printed model of the same thing. So what you can see here is a central atom and then all 4 of the peripheral atoms. So this one does require 3 dimensions in order to actually get this shape correct. So oftentimes you'll see it sitting, and then when it's sitting, oftentimes this is going to have one where you've got some of it sticking out at you, some of it going back behind the page, and then 2 of these then in the plane. And we'll take a look at how we can represent that and draw that. This is also one where I have to admit the clay model is difficult, because in a perfect world, I would have these 2 top in a plane and these bottom ones would also be in a plane, but you can kind of see this is not perfect and it's a little bit squished, because the goal is to get all 4 of these 109.5 degrees from each other, which is just not the easiest thing to do with clay. But again, you should be able to turn this so that 2 of these are in a plane and the other 2 are also in a plane. So again, it's a little bit tricky. For tetrahedral, one of the most fun parts about tetrahedral is that there's lots of ways to represent it. So if my torso, my body, is the central atom, I can go ahead and have my 2 hands go ahead and be other atoms, and I can put those out far of me. And I'm basically pretending that I'm going to be in a box. So I'm going to go ahead and put myself in my nice little mime box where I have a top and a bottom. And all of that. So then, because I'm in a cube, I'm going to go ahead and put my 2 arms about in opposite vertices of this, and I'm going to put my feet in the other ones. So this then is going to give us that tetrahedral shape where I have my 2 hands in one set of vertices and my feet in the other. And this will actually give us our tetrahedral shape. 4 is one of the more difficult ones to visualize. But this is also one of the most important because this one comes back a lot. As you may have noticed, carbon is a big fan of having 4 bonds. So we are often going to be looking at things that have this tetrahedral shape overall. So our bond angles are this 109.5. The way we get that is essentially if we have a cube, pretend that's a cube. If we were actually to have our central atom in the very center of this cube, and then we would have our peripheral atoms at opposite faces, at the opposite vertices. So here's my bond my electron domain trying to go in between there. But then instead of it being on the same places, I'm going to draw these on opposites. So it will then be on that opposite side. So down over here. My drawing is not excellent. But notice in here that all 4 positions then should be equivalent. So where I actually am now is I am in a PhET simulation that is called Molecule Shapes. And what I can actually go ahead and do is give this my number of electron domains that I might have. So this is it with 3. I'm going to go ahead and add the 4th. And what I can now do is I can go ahead and rotate this. So it's a little bit wiggly, which isn't so bad. But then you can kind of get another feel for what this might look like in 3 dimensions. This also will go ahead and name things for you. And this will also go ahead and show bond angles. So that way we can go ahead and take a look at where our bond angles might be. And again, they are going to move as I rotate this molecule around the screen. But this can be another useful tool for helping you guys get a handle on what these really look like in 3 dimensions. Notice that they're using shading and shadows to try to get the notion that some of these are coming out at you and some of these are going behind. When I draw these, which is coming up right next, notice that I can have this in different setups where either I can have these 2 in a plane and then one coming out at me and one going behind, or I can draw this in more of that way that looks like it's a little tripod where I have 3 on the bottom. But notice that when I do that, I still have 2 in the same plane, and I still have one that comes out at me and one that goes behind. So let's take a look at how we're going to draw that. So again, we talked about the fact that there were 2 different ways to draw this. I'm going to start with that last one, where I have a central atom, and we're drawing all 3 on the bottom. So I'm going to show something coming out at me as being a wedge, and something going behind the page as being these dashed lines. So I can do that other one, where I had basically 2 up and 2 down. And then again, one is going to be coming out at me, and one is going back behind the page. So again, your wedges come out at you, your dashed lines go back behind you. I frankly think this is in part because as scientists, we don't usually have a lot of background in drawing or in art, so our ability to show perspective in shading is not fantastic. So therefore, we are going to use dashes, wedges, and straight lines. So lines being in the page, wedges coming out at you, dashes being behind. We are going to go ahead and call this tetrahedral, and all of these are going to be 109.5. And just for fun to point out a comic strip that I really like is 9 Chickweed Lane. This is an old one back from 2001, but this is again trying to show perspective. So in the plane is where the comic strip actually is itself, or would actually be the upper body of the character. And then you have the two legs, one that's trying to come out at you and one that's actually going back behind. So perspective and showing one bigger than the other is how artists would do that. Again, chemists, not artists. So coming out at you is going to be the wedge, and going back behind you is going to be a dashed line.
I can hear you, but I won't. Some look for trouble, while others don't.
5. So we are going to have basically a trigonal planar shape. So you notice I've got my 3 matches that are sticking out of this that are supposed to be 120 degrees from each other. But then in addition to that 120, I also have sticking straight out, then I also have 2 safety pins. So these are supposed to represent, the matches are supposed to be my equatorial positions. So I can actually get this lined up properly. My matches are supposed to be my equatorial positions, and my pins are supposed to be my axial positions. So the 3 matches are my equatorial, like the equator around the middle, and the top and bottom are my axial positions. The balloon model still works, but the balloon model starts to get kind of bulky. So again, I've got 3 balloons trying to represent in the middle my equatorial positions, and then my axial are that green and yellow one above and below. You'll notice that the balloons are not doing nearly as good of a job as being exactly apart from each other, which is a little bit of a problem. So the balloon model is not really my favorite for the 5, but there is actually one more way to represent this. For 5 electron domain geometries, this one also gets a little bit tricky, but again, we have our equatorial positions that are here represented by markers, and then I need my 2 axial positions. So what I can actually do is go ahead and put one there, and then the bottom one down here. So again, I know it's a little bit awkward to go ahead and hold 5 different markers all in one, and I have problems getting that other axial position in there without another hand, but you can actually look at then the different positions really well in this way, and our dog is protecting us as we speak. Good boy. Protect my axial positions. Our next shape is trigonal bipyramidal, trigonal bipyramidal. There's different ways to say this, they all work. But notice that what you're going to have here is, again, those equatorial and axial positions, where my equatorial are going to be 120 degrees apart from each other, and my axial will be 90 degrees from my equatorial, 180 degrees from each other. So there's a lot of different ways to look at this molecule. So it's a good idea to, again, try to take a look at this. So when we look at 5 electron domains, what you'll notice is that we still are going to have our 2 axial positions going up and down, and then we have 3 different equatorial positions. This set of bond angles that's shown right now are the bond angles in between my axial and equatorial electron domains. What I want to go ahead and do, though, is I can rotate this and basically hide my axial positions. And now what we mostly see are the equatorial positions. So then you can see the 120 degrees in between each of our equatorial positions. As we go to draw this, we often are going to draw it in this way that lets us see all 5 atoms at the same time. What you hopefully can see is that 3 of these are actually in the plane together. So both of my axial positions and 1 equatorial position are all in the same plane, leaving me then to have one of my equatorial positions coming out at me and one of my equatorial positions going back behind the page. So drawing that then, central atom, axial up, axial down, equatorial out, equatorial coming out at you, and equatorial going back behind the page. And again, we've got 2 different sets of bond angles. I have some of these representations here because this notion that it's bipyramidal, you're like, so where is the pyramid? Where did that go? So a lot of that comes from if you were to essentially put faces on these. So these are shown basically as if the structure itself was inside of some sort of prism. And that outside prism shape would actually give you two pyramids that have a triangle as the base. So in the trigonal bipyramidal, if you really wanted to, you could think about this as two pyramids. So here's one pyramid on the left, here's one pyramid on the right, and if we put them one on top of each other, you then get your bipyramidal shape, where you actually, whoopsies, I did not glue these together. You actually have all 5 of your electron domains, with my axials being represented by my 2 fingers on those vertices, and then there are in fact 3 in the middle.
There's 1,000 reasons I should go about my day and ignore your whispers, which I wish would go away.
My octahedral geometry with its 6 electron domains is again nice and useful to do, should be 90 degrees from each other. This is another time where to get that octahedral idea, you would actually cover all of these faces. So there are actually 8 faces here, even though there's only 6 electron domains. And here's my balloon model. So again, I've got the 4 in the middle, 1 up, 1 down, or again, 4 in the middle, 1 up, 1 down, but they should all be equivalent to one another. So this is Love Jack. So this is actually on campus. Kudos if you guys can figure out actually where we are. But what I'm going to do is walk around. So essentially you can see that the central atom would be that part in the middle, and then you would have coming out from it 6 different peripheral atoms. If you've never seen one of these before, this is an 8-sided die, also known as a D8, but this actually gets you an idea of why that shape is called octahedral. So essentially everywhere there's a point, not a face, but a point, is where we would have one of our electron domains sticking out, and the central atom would be in the center. And again, you actually do have those 8 faces. So they are all on here, but yeah, this is an 8-sided die. And this is actually how we get the octahedral name. Last one is octahedral. This isn't going to have bond angles of 90 degrees, all positions equivalent. These do look like jacks. This is where the Love Jack used to be. So this is a picture of UT Dallas. So this is actually about how we're going to try to draw this. But again, notice we could put this end on end. And oftentimes if it's end on end, then we could actually make it look like it's really nice because it's a lot of 90-degree angles. Lots and lots and lots of 90-degree angles. So in doing this, there's a lot of, again, different ways to represent this, but we're going to show off with essentially 2 coming out at you and 2 going back behind the page. And I know those bond angles keep changing. That's because I keep wiggling things. So whenever I wiggle, the program is trying to still show me my bond angles no matter what. So if I get rid of those, it's not so bad. But yeah, this is wiggly because I can basically move this around. So I do recommend, the nice thing with this PhET simulation is this PhET simulation is actually in HTML, so it's a lot easier for you to work with it yourself. Coming around to my drawing, central atom, 1 up, 1 down, 2 that come out at me, and 2 that go back behind the page. And everything is 90 degrees from each other. That gets us through our electron domain geometries. So we're not done yet because you may have noticed that we left this column all alone, but that does get us through the base set of electron domain geometries. So the good news is this is a solid foundation to start from.